Okay, hello everyone. My name is Ali. I'm doing my master's in Polar Lab, and today I want to talk about one of the most important methods that we use in the lab to solve our problems, which is system identification. And I'm going to introduce one of the most commonly used and basic methods of system identification, which is a building block for most other advanced algorithms that we use. So to begin, I would like to say that a lot of real-world systems that we are interested in are highly complicated to analyze because they are classified as dynamic systems. I'm going to explain what that is in a moment, but we can look at systems such as man-made systems, such as fighter jets, complicated systems such as the economic systems and financial markets, and natural and biological systems like the human body and the human locomotion system and the human motor control. These are all classified as dynamical systems that are hard to understand, but they are also very important for us because we need to understand their dynamics to be able to control them, to manipulate them. We need to be able to predict the outcome of these systems. And we are also interested in understanding the inner workings because in our case, in biomedical engineering, they are related to the health of patients. So first, I'm going to talk about the term dynamic. So what does it mean when we say a system is dynamic? So I'm going to use a little bit of mathematics here because I believe this is a more intuitive way to do it. So a static equation or a static relationship is a relationship between two variables such as x and y on the top, where the value of the output, which is y in this case, only depends on a specific value of the input. So whenever we want to find out the value of y, all we have to do is to plug x into the relationship and we will find out the value of y at that particular x. This is called a static relationship or a static system. But dynamical systems are more complicated because they involve time derivatives. So we can see in the bottom equation that we have second and first derivatives, time derivatives of our input. So this means that at each moment in time, our output not only depends on the current value of the input, but also on the past value. So in some ways, the system has a memory. The system manipulates its previous inputs, previous moments to output the value. So this is why finding the description of such systems is more complicated. So, okay. So how we approach static models or static systems is using common methods that we are all familiar with, such as regression or neural networks. These are all approaches for modeling and identifying static systems, because using this type of approaches, we can understand the input-output relationship of these systems. However, unless this is a specific architecture, such as a recurrent neural network, we are not able to understand the sequential relationship between the input and output, because we are not considering the time derivatives and past values of the input. So what do we do when we face dynamic systems is we use a method such as system identification, which is basically testing the system and giving it different inputs and observing the output, then using this data and some algorithms to understand the input-output relationship or dynamics. So for example, when people want to understand how to control fighter jets, although this is a man-made system, but in the real-world application, it's a complicated thing to understand because with time, the characteristics of system change. So it's always important to have a really accurate understanding of the dynamics. So as I said, the main idea is to feed inputs into the system and observe the output and then try to figure out what's the system doing to the input. So, and this, the right picture is the problem that we are working on in our own lab, which is trying to identify the system, which is the human neuromechanics, and with where the input is the position of the ankle and the output is the torque. So this is the general idea. Regarding the third example, which is financial markets, since we do not know the input of the system, people usually use other manipulated versions of the output signal as some other representation to be able to estimate this basically time varying systems. Anyways, so today I'm going to talk about the impulse response function, which is a specific algorithm and method for system identification. It uses input-output data to estimate to identify the system behavior. It assumes a linear and time invariant system. I'm going to explain what that is in the next slide. It's a simple and very efficient method and model structure to identify the systems, and it can be used as a foundation for more complicated and complex algorithms. So just a quick overview of what it means for a system to be linear. We call a system linear when something called the superposition principle is acting in the system. This means that if we give the system a specific input like x1 and we observe the response, and then separately we give it another input like x2 and observe the response to this input, if we give these two inputs simultaneously, like sum them and give them to the system, we will observe the summation of those two separate inputs. So if we observe this in a system, we say the system is linear. And this is a depiction of what I just described. So as you can see, for example, the top left input has the top right output. And if we summate all these inputs and the output of this black input is the one showed in the bottom right, then we can assume that this system is linear. However, linear systems are actually non-existent in the real world, but we can approximate complicated systems in small ranges to be linear. This is a very important idea in the method that I'm going to describe. Another important concept is the concept of time varying behavior, which means that the input-output relationship itself varies with time. So again, for the IRF, we assume that our systems are not time varying and they are time invariant. This means that the dynamic relationship between input and output stays the same as time goes by. This does not mean that the system is static. However, it means that this time-dependent relationship itself maintains its format throughout time. So it's important to know, when we want to approach this type of problems, it's important to know that there's always an issue called noise, because we're dealing with real world physical problems. So the input then and output that I've been talking about so far are also ideal constructs, because the input is always contaminated with sensor noise and the output is also like that. So we can never know what the input and output are, but we will always have a noisy, distorted version of them. So whatever method that we develop and we try to use has to be robust to noise, because noise is always there. And if we have a method that works good in the absence of noise, it will not be useful, because we cannot get rid of noise in the real world situation. So what is the impulse response function? The impulse response function is the response of the system to an impulse, which is a very recursive definition, but I'm going to explain it now. So an impulse is basically a very sharp and fast and quick jump in the value of the input. And this is also a mathematical construct, but in the real world, we can imagine it to be a very sudden shift and a sudden move in the value of the input. So when we give the system an impulse as its input, we can observe the output as it unfolds through time. And this gives us something like a fingerprint of the system where we can gain a lot of information from. Because although we only have the output of a single impulse, which is the IRF or impulse response function, we can actually describe any arbitrary input as a summation of a bunch of these tiny impulses. And since we assumed linearity and time invariance in our system, we can find out the response by summating the impulse response function through this through the time domain of this input. I'm going to so this is what I just described. So we can basically describe any arbitrary input as the summation of impulses. And when we give this summation to our system, we will observe that the output is in fact dependent only on the impulse response function. So in other words, if we have the IRF or impulse response function, we can predict the output of the system for any arbitrary inputs, even if we have not seen it before. And this is a very important thing, and this is our main goal, because this is when we can claim that we have identified the system, to be able to predict the output to a novel input, basically. So how can we estimate and how can we acquire this IRF? There are many ways to do this. Well, one might first ask that, okay, since the IRF is the response of a system to an impulse, let's just stimulate the system with an impulse and watch and look at the output. That would be the impulse response function. Although this is correct, but in the real world, again, in the real world setting, this will not work because we are never able to provide a physical system, like a mechanical system, with a spike, because it's difficult to generate, it's dangerous, it could be invasive, it could harm the system. Furthermore, because you're always dealing with noise, this type of short and tiny and low power input will not give us a rich enough input to be able to overlook the effects of noise. So when we have such a tiny input, the effects of noise will dominate and we will not be able to estimate. So this is not how you do it. But one of the best methods to do it is based on the input-output cross-correlation. So basically all this math here is showing that if we cross-correlate the input and output of the system, if we calculate the cross-correlation, we will get a term which is really easy to estimate, which will easily give us the impulse response function. So if we cross-correlate the input and output, we will have a good estimate of the impulse response function. Not only that, but as you can see in the middle set of equations, this approach is really good in handling noise, because when we cross-correlate input and output, since the noise that we talk about is Gaussian noise and it's uncorrelated, some terms will cancel out, so the effects of noise won't be that drastic. So this is very good news, because it's important to be able to handle the noise. So this is how we identify the IRF, and this is what an IRF is. But as I said, none of the real world systems are linear, nor they are time invariant. So what use is the IRF to us? Because all the systems that I described are very complicated and highly nonlinear, but the IRF is only an LTI method. So why do we use it? The answer is there are ways that we can use the simple IRF to estimate these highly complicated systems. For example, we can estimate a time-varying IRF, meaning we can estimate a single IRF for each instant in time, and then we will have this three-dimensional model, which gives us a particular model for each instant of time. This is how we can understand, how we can predict the output of a time-varying system using the IRF. Furthermore, we can use a parameter-varying IRF, which is an IRF which is dependent on the parameter, any parameter that we're interested in. So in the case of our experiment is the ankle joint position, we can use this type of approach to estimate an IRF for each particular value of our parameter and use it to predict the time series, which is the output of the system. As you can see in this paper, which is published by Ehsan Sobhani, the VAF or variance accounted for, which shows how accurately the model is predicting, is at 91% for this very complicated neuromechanical system, using an advanced algorithm, which is but essentially based on the IRF. So to conclude, the IRF is a very simple method for modeling LTI systems or linear time invariant system, or we can use it for small signal analysis of these complicated systems, as I described. Furthermore, the number of parameters that we deal with when estimating the IRF is usually very small compared with other approaches such as methods used in machine learning. And depending on the memory of a system and depending on the characteristics of a system, for example, a time varying IRF could have as a maximum number of like 100 parameters, whereas trying to train a recurrent neural network to predict the outputs for a time series will have a lot more number of parameters than this type of model. Thank you very much for your time, and yeah, that's the presentation.
Okay, perfect. Maybe you can keep your presentation so we can can ask questions.
Of course.
From the members. Do you have any questions, guys? No questions? So if there is no question, I'm going to go and ask. Yeah, Olivier, please.
I think Olivier.
Yeah, I'd have a question. I'm interested in, do you have a basic answer to, if somebody was to ask you what's the basic difference between an AI learning algorithm that would determine the relation between the input and the output and what you're doing with the multiple IRFs?
Okay. So Dr. Moebi and Amir are definitely more qualified. Do you have my?
Sorry. You should unmute, and I'm gonna mute Olivier because you're gonna have an echo.
Okay. So as I said, Dr. Moebi and Amir are really more qualified in this than me. But as far as I understand, one of the most key features of system identification is that we give the system the input that we desire. We design an input based on our algorithms, and we feed it to our system and then observe the data. Whereas, I believe that for most learning, like supervised learning, we are always given some data, or we collect some data. We cannot stimulate the system with our desired type of input. This is like one main difference that I've noticed between basically identifying this type of model. And another difference could be, as I said, even CNN or deep neural network, they are still static models. They're not for time series. But I guess we have like LSTM or recurrent neural networks that are used for estimating time series. But so the main differences is that system identification is usually used for physical systems, real world physical systems, and the fact that we are the ones that give it the input. So we are able to test any type of input that we want on the system, based on the restrictions, and then look at the response. And they usually have a lot less number of parameters, but they're really similar, essentially. All you do is you feed data to the algorithm, data-driven, and find the model. Also, another important distinction is that not the IRF, but a lot of other approaches in SysID are parametric. So you can use our prior knowledge of the system to design a model structure that is correlating with the problem. So when you estimate a bunch of parameters in neural network, they are not correlating with any real world variable. But with parametric models, for example, when we estimate this parameter in the model, this is actually like the stiffness of this muscle. Yeah. So that's useful. I don't know if maybe I didn't answer it, but
yeah. That was a good answer. So what Ali was trying to say was that when we're using basically parametric system identification, we have a model structure. basically a model that represents the physics, the dynamics of the system. And then from this model, using the system identification approaches, we're going to identify the characteristics, the parameters, the values. But with all black box approaches of deep learning, machine learning, it's completely a different story. I have another question. Actually, you answered the first one because you started your presentation saying, okay, so we have a dynamic system, machine learning algorithms are not capable of doing that. And then you explained, yeah, we already have some recurrent system, recurrent neural networks that are capable of somehow predicting time series and time-varying systems. But there goes my second question that goes directly towards the impulse response function. You explained to us in simple terms that the impulse function is important with the linearity, the superposition characteristic of a linear system. We can basically superimpose the responses to different impulses that estimate the system, that basically put the system together. But from the beginning of the story, why an impulse function? Why not another function that we can use?
Okay. So we are, I mean, there are other functions that are used, like the step function or the ramp function. They're always used in system identification. But the reason that impulse is attractive, because the Fourier transform of the impulse is 1. Like the Fourier transform or the Laplace transform of the delta function is the number 1. It's like it's representing 1 in the S domain. That's why it makes all these equations really nice and very easy to work with. For example, for the reason that let me see if I can show anything useful here. So right here, when when doing the cross correlation between the input and output, because the impulse, the H, which is the impulse response, is the response of the system to a delta function, all these terms is as if they are being multiplied by 1. When we're doing the convolution sum, it makes everything very simple and very easy, and we're able to isolate this H. Because if it was a different type of response, we would have other terms in these equations, and we wouldn't be able to we would be able to estimate it, but it wouldn't be as this clean. I mean, I guess that's my understanding of it, because delta is 1 in the S domain. It's really easy to work with.
Do we have any other question from the team? If no, I'm going to go with the last one. So from the Fourier theorem, what we can do is that the theorem tells us that we can approximate pretty much any function with sums of sinusoids. And then if we apply this theorem to a system, to a linear system, like the one that you explained it, we can get the response as separate responses to each sinusoid and then sum them together. So the same rule as you explained it for the impulse response applies to the sinusoidal impulse, to sinusoidal inputs. Is there any relationship between these two things that I said? The Fourier theorem or the sinusoidal inputs and the impulse.
Exactly. I mean, yes, that's a different kind of identification, which is called frequency response functions, which is actually the frequency domain version of the same idea, because when we try to do a frequency response, we'll try to derive the frequency response, identify the frequency response function. The ideal thing to do is to give the system a white noise, a white input. Just since I said that if we want to do an IRF, we have to give the system the impulse, But in the frequency domain, we should give it the white noise, the white input, because it contains all these sinusoidals. It will be the best identification. But the interesting thing is that as I said, the Fourier transform of the delta is a constant, which is exactly the white input. So if you look at the frequency spectrum of the delta function, which is just a spike, the frequency spectrum is a constant number, which means it's a signal that contains every single frequency in the universe with the same amplitude, which is exactly what you said. So if we want to get the frequency response of a system, we give it all these different sinusoidals from like 1 hertz up to infinite gigahertz, not practically, but in theory. But if we sum all these sinusoidals, we will get this constant number, which is the delta function in the frequency domain. So these two ideas are exactly the same idea, but this is time domain version, and the frequency response is the frequency domain version of the same.
Perfect. Great answer. And now, since Amir has passed 502 with Professor Carney, I'm going to ask this question from Amir. So what is the mathematical relationship?
What do you mean by with the mathematical?
Between impulse response and frequency response, there was a relationship between these two. So the Fourier transform.
The Fourier transform of the okay, yeah, the Fourier transform of in the S domain is equivalent to the convolutional integral in the time domain.
Okay.
Yeah.
Okay, so we leave it to that, but there is a more close answer. Ali explained it a while ago, but there's a more clear relationship between these two things. Actually, from one, you can obtain the other one.
Yeah.
It was explained in 502. Okay, perfect. So thanks a lot for the excellent presentation, Ali. It was really informative. I really liked it. I hope the other members and other audiences who will see the recording of your presentation like it as much as I did.
Thank you.
Perfect.